Good morning, class. In the last class, we talked about the composition of programs in terms of the assignment, the alternative, and the repetitive statements. And we also learned about what are called preconditions and postconditions. We saw a few programs about that, where a precondition is an assertion that is true before a program is executed, and a postcondition that becomes true after the execution of the program. So proving correctness implies we start from the precondition, and as every execution of every statement changes the state of the variables, and the execution of these statements corresponds to the actions, the values that are changed in the variables correspond to the states, and ultimately, starting from this initial state, we want to reach the final state. And what we want to ensure is that the sequence of statements that we have written as part of the program actually takes us from this initial preconditioned state through the execution of the statements to the final state. So today, what I'm going to do is I'm going to talk about the proof rules that are there for we talked about the fundamental programming constructs that we have, uh, essentially the assignment, the alternative, and the repetitive statements that make up a program. And today we will talk about the proof rules that will enable us to prove correctness or properties of programs where it consists of assignments, alternative, and repetitive statements. Okay. So what I'm going to do is I'm going to write this down as I go along. I hope you can see my iPad on the screen. And so what is a proof rule? A proof rule is a pattern of reasoning that will assist in proving the properties of a program. Okay, of a program. All right. And proof rules in this course will take the form H1, Hn, then H. What this essentially states is that this states that if H1 up to Hn are the true assertions, then H is a true assertion. So what we mean by this here, above the line, we have a set of assertions which are true. And if all these assertions are true, then the assertion in the denominator is true. Okay? Let us look at two simple rules of inference. Rules of inference, okay? So we'll start with rules of inference for each one of the types of statements. Let us take a simple form. If I have an assertion P that is true before a sequence of statements or a statement is executed, and this leads to the assertion R, and we also have that the assertion R implies Q, then the proof rule, what we can assert is that P S actually asserts Q. P is the precondition for the sequence of statements S leading to the post condition Q. P is the precondition here, Q is the post condition here. Notice that what we are telling in the numerator is that Pre is the post condition for R, where S is the sequence of statements. But we know that R is the precondition for some other assertion, Q. Then we can safely assume that P is the precondition for the assertion Q. Execution of a program ensures the truth of this. Truth of R. Then execution of a program S ensures the truth of R. Then it also ensures the truth of every assertion implied by R. That's what this uh, proof rule means. Now, let us consider an example. Let us assume that we have variables int x, y, u, and z that are defined. Okay? So declaration of variables is done as part of the function specification of the program. Then, if we have this precondition, x greater than 0 and y greater than 0, and a statement is executed, and if we can assert after the statement is executed that z plus u star y equals x star y, and u equals 0. So what is it that we have? We have here a precondition P, have a precondition P here, and this is S, and then we have a post condition R over here. Okay. Then let us look at this second statement here. We have Z plus U star Y equals X star Y, and U equals 0. Clearly, what does this imply? This, if I take this as a precondition, this clearly implies that Z is equal to X star Y, because U is 0, and this is simple arithmetic expression that we are looking at. So this is R over here, this is Q over here. So from this, so what happened? We started off with P, we executed a set of statements which led us to assert R. Suppose this is what we saw, assert R over here, and what we're saying is this R Clearly, from this statement, z plus u star y equals x star y and u equals to 0. So if u is 0, this term becomes 0. Therefore, z equals x star y. Therefore, we can assert that z equal to x star y. Then, now we can say the proof rule is as follows. That is P S Q. That is what this inference rule means. That means, what does it mean over here? I'm saying x greater than 0 and y greater than 0. Execution of the statements S leads to the assertion Z equals X star Y. Okay, this is the rule, and this is a very this is called this one simple rule of inference. Again, to recap, what is it that we are saying? If we say that if this is the precondition and after the execution of a set of statements, we can assert a postcondition R, and this postcondition R implies an assertion Q, then we can conclude that the precondition P after the execution of a set of statements results in the postcondition R. And we saw this again with an example where we said, let us assume x, y, u, and z are integers which are defined. So as part of the functional specification of the program, this is primarily declaration of variables. And if x is greater than 0, y is greater than 0, a sequence of statements are executed. And after the execution of the sequence of statements, we can assert that the variable z plus u star y equals x star y and u equal to 0. Then from this R, we can surely assert that z equal to x star y. This implies this primarily because u is 0 and you get z equal to x star y, applying the rules of arithmetic. Okay. Here we are applying the u equal to 0 and we can prove this. So what does it tell us essentially? That the rule of inference, what we can conclude is that the precondition P after the execution of a set of statements S results in the postcondition Q. Okay? So let's look at one more simple rule. We call it B over here. And what the state is somewhat different. You see, if P implies R and R S Q, then we can conclude that P is a precondition sequence of statements, and you can assert. Okay, this is another rule of inference. So what we are saying is, if here, what do we mean here? If R is known to be the precondition for a program S to produce Q, after the execution of S, S then so is any assertion that implies R. That means, what is it that we are saying here? We are saying that we know that R is a precondition for a sequence of statements S, and execution of the programs leads us to produce the assertion Q. Then we have some assertion which implies R, in this case P over here. Then we can safely conclude that P is also a precondition for the sequence of statements for a program S leading to the assertion R. So now what is it becoming here? P now is a precondition for S. Okay, this is the important takeaway. Let us again take an example. Suppose we have this declaration again. The variable declaration as before. Okay, writing a program again. So you first do the variable declaration. And let's say I have int x, y, q, and r. Again, we will assume all are unsigned integers. And let us look at the statement. X equals y star q plus r and 0 less than or equal to r, strictly less than 1. What is this? If this is like, what are we saying? Q is the quotient when x is divided by y, and r is the remainder. Now we have seen this again and again. Let us call this P. Now, suppose we use the rules of arithmetic. Then I can say x is equal to y star q plus 1 plus r minus y, still 0 less than r less than 1, r less than y. So this is our r. Okay. So basically all that I'm doing is add y, subtract y. So I'm actually not changing the equation. Okay. So what we're saying is P implies R using the rules of arithmetic. Okay. Now let us see what happens if I execute the following statement. Now I have, let us take the post condition that I have, that in implication, the assertion that is implied by P. I have x is equal to y star q plus 1 plus r minus y. This is our r over here. And suppose I execute the statement r equal to r minus y. Then what do I have? I have here x is equal to y star q plus 1 plus r. So this is r over here and this is q. Clearly this is an arithmetic expression that I have simply this in this arithmetic expression. I have simply replaced r with r minus y. Here it is using, r is using the old value of y, old value of r, whereas here q is using the new value of r. Okay. So now we can safely conclude this. This enables us to deduce that x equal to y star q plus r and 0 less than or equal to r less than y, and the execution of the program r equals r minus y, this is p here, can lead to the post condition. The q then becomes x is equal to y star q plus 1 plus r. Okay, so again I repeat, let's go back to this example. What is it that we are looking at? This is the second implication rule. What it says is that if r is known to be, we know that r is the precondition for a program S to produce the post condition Q after the execution of S, then so is any assertion that implies R. What we mean by that is any assertion that implies R is also a precondition for S. And we took a simple example where x, y, q, and r are all unsigned integers. And we said x is equal to y star q plus r and 0 less than or equal to r less than y, because that's the meaning of the reminder here. Then this implies that x is equal to y star q plus 1 plus r minus y. I'm simply using the what am I doing over here? I'm essentially okay, what we're doing over here is the following, that